So here we go, Green's theorem. The goal is to use Green's theorem to evaluate line integrals. First note, a curve C in a plane has a positive orientation if it is oriented in the counterclockwise direction. So what do we mean by that? The curve, and we're going to be talking about closed curves mostly here. So I'll go ahead and draw in a closed curve. This would be a simple closed curve because it doesn't cross itself. So as opposed to a figure eight, that's a closed curve, but it crosses itself in the middle somewhere other than the endpoint. So if you consider this the endpoints, it won't cross itself anywhere in between as you travel along the curve in this case, a counterclockwise fashion. Okay? So looking down on the XY plane, if you see an ant traveling along that curve and it's moving in the direction indicated by those arrows, then it's positively oriented. The ant is traveling in the positive direction around that curve, okay? So it's kind of like, you know, how we measure positive angles versus negative angles. If you turn the terminal side of the angle in the counterclockwise direction, we consider the angle positive. Clockwise, it would be a negative angle. Okay, so let's talk Green's theorem. So let C be a positively oriented, piecewise smooth, simple closed curve, which means it doesn't cross itself. No figure eights here. That bounds a region R in the XY plane. So then in my picture above, R is inside here. That's all we're saying. Okay? So picture that kind of curve. Then, and here's the upshot of everything, then as long as P and Q have continuous partial derivatives in an open region containing R, that just means everything's well behaved. We can say this, that the line integral over C f dot dr, so that's the line integral with respect to a vector field. Okay, just to review it, we're in the plane, so what would the differential form of this look like? Integral over C, P and Q are the components, so you could say P dx plus Q dy. That means exactly the same thing in a different notation as integral over C f dot dr. Both mean the same thing. The first one is just the generic notation we came up with originally for the line integral with respect to the vector field. The second one is called differential form. So that's not really the conclusion. Here's the conclusion, that the line integral is equal to a double integral over R, that region that C encloses. It's the double integral over R of dq dx minus dp dy. Partial funky d's all the way, partial derivatives all the way, right? dA. And that's Green's theorem. Why do we care? Because sometimes it will be much easier to evaluate the double integral than the line integral. Okay, let's do a quick example before I do a partial proof of Green's theorem. So let's do this one. Let's evaluate the line integral over C of negative y dx plus x dy over the triangle given by x equals 0, x plus y equals 1, and y equals 0. So this is going to give us C. C is going to be composed of 3 line segments. Let's graph that real quick. So graphing x plus y equals 1 first, it's going to have intercepts at 1, 0 and 0, 1. And then x equals 0, that's just going to be part of the y-axis there. And y equals 0 will be part of the x-axis there. And so C is comprised of these 3 line segments. But we'll go ahead and use Green's theorem to evaluate this so that we don't have to integrate over, well, 3 separate segments, right? That's how you'd have to do it if you were integrating directly. So Green's theorem says that the integral over C of P dx plus Q dy is equal to the double integral over R. R is the region enclosed, in this case, by these 3 line segments that comprise C, with an integrand of dq dx partial q with respect to x minus partial p with respect to y dA. So let's just compute dq dx. Well, if you think about it, this guy is q, so dq dx is 1, and dp dy, well, this guy in this case has to be p, so the derivative of negative y with respect to y is just -1, and so if we take dq dx minus dp dy, that's just going to be 1 minus -1, 2. You're going to have an integrand of 2. And then if we go with a differential order of dy dx and a vertical, so that means a vertical representative rectangle, remember. And if you think of this line segment, the slanted line segment, as, well, just solve for y. So y equals 1 minus x. Then the inner limits of integration go from 0 to 1 minus x. And the outer limits of integration go from 0 to 1. Now, we could just pull this 2 out front. And then, since the integrand then becomes 1, this integral represents, so this integral represents the area of this region. This is just a triangle with a base of length 1 and a height of 1. So the area of this triangle is 1 times 1 times 1/2, or 1 times 1 divided by 2. Either way, it's a half. And so we get 2 times a half, or just 1, for the value of the line integral.